So the Squeeze theorem, and before that I said we have a preliminary theorem, which goes like this. If if f of x is less than or equal g of x near x equals a, okay, and in parentheses, except maybe for except for x exactly equals a, that's possible. As you know, the limit can exist, but the function doesn't have to exist at x equal a. Then the theorem, this particular theorem says that the limit of f of x as x approaches a has to be less than or equal the limit of g of x as x approaches a. Okay. And provided that both limits exist. Okay, so look at it for a second, and it does make sense. If you have one function sitting underneath another function, and that function may be continuous or may have a hole or some kind of asymptote at x equal a. So for every point near a, except for a itself, then the limit of the function that is sitting below the other function, the value of that limit will be also less than the value of the limit of the function sit above it. Okay? So it's kind of something that intuitively you can accept, right? We don't prove this theorem right now. We just going to take it, okay, it does make sense, we'll move on. So now comes the actual squeeze theorem. The squeeze theorem, we're dealing with three functions. It's also called the sandwich theorem because one function is sandwiched between two others. So it goes like this. Pretty much the same thing. If you have three functions here, f, g, and x, arranged such that f of x is less than or equal g of x, and g of x is less than or equal h of x. Right? Near x equals a, so 5-minute warning. Again, except perhaps for x exactly equals a, and. So we have another condition here. Instead of one if, we have another one, and the condition is the limit of f of x when x approaches a equals to the limit of h of x when x approaches a. And they're both equals to a certain value, let's call it L. Okay? So what happened is, remember, of the three functions, the two outside functions, f and h, g is in between these two, but the limit of f equals the limit of h, then it stands to reason that the middle function also has to equal L. And this is the conclusion of the theorem. Then the limit of g of x equals L as well. Okay? So what is the picture here? One picture that we can draw to kind of make sense out of it. Let's say this is x equal a, right? So this is x and this is y. And you have one function, let's call it, this will be our f of x. Okay, so this is f. And then you have another function, let's call it g. And in between, there is a third function that may do all kind of crazy stuff like this. I'm sorry, this is h, this is g, the middle function. Okay? So this is h. And you see right here in this area, h is greater than g and g is greater than f, but the limit is the same. Now, the function may not exist, so we may have a hole here, but the limit does exist. Okay? And a quick example, classic example, you may have it in the homework. Let's evaluate the limit when x approaches 0 of x squared sine of 1 over x. Okay. We cannot use the product rule, right, because the limit of sine of 1 over x does not exist. 1 over 0 does not exist, so we don't know what is the limit. So we'll write we cannot use the product law. Because this limit does not exist. It's easy to see it. On the other hand, we can say the following. We know that sine of any sine function, sine of any function, even 1 over x, will be bounded by negative 1 and 1. Okay? The sine function going to always be a value between negative 1 and 1. So we'll take this relationship, and this is the key thing with the squeeze theorem. You want to have like a compound inequality where you have 3 terms. Okay, so what we'll do now, we'll multiply this inequality, this compound inequality by x squared. Okay, and if you multiply, you get negative x squared less than or equal x squared times sine of 1 over x, and less than or equal by positive x squared. Okay? So now we're going to say, if I'm looking at the squeeze theorem right there, this will be my f of x, this will be my g of x, and this will be my h of x. And I'm looking at something like this. Okay? So I have this condition for the squeeze theorem. And what else I know? I know that the limit on the left, the limit of f of x, when x goes to 0, which is the limit of negative x squared when x goes to 0, well, this is a direct substitution. It's 0. On the other hand, the limit of h of x when x goes to 0, which will be the limit when x goes to 0 of x squared, is also 0. So the limit on the left and the limit on the right goes to 0. So now we can say that the limit of x squared sine of 1 over x is bounded between the 2 zeros here and here, and therefore the limit of x squared sine 1 over x, like so, has to equal 0 by the squeeze theorem. And that's completed. So this is an example of how you use the squeeze theorem. And I can tell you right away that you have a fair chance to see a question like that in the first test. I may be 2 minutes over, so let me take a question.